Today we will talk about the basics of germicidal UVC and specifically how UVC energy can inactivate airborne pathogens. Infectious disease experts and building science professionals recommend 3 scientifically proven means of reducing pathogen spread: ventilation, filtration, and germicidal ultraviolet light systems. So UVC is one of 3 engineering control strategies that scientists and building engineers endorse to reduce infectious diseases. We will explore the 3 main ways UVC is applied in HVAC applications, including airstream disinfection, upper air disinfection, and HVAC coil maintenance systems. Once we understand how germicidal UVC can be delivered, we'll look at ASHRAE's position on ways to limit disease transmission. We'll close by looking at how air cleaning technologies might be combined to offer a layered approach to infection mitigation. First, let's look at the basics of germicidal UVC. The electromagnetic spectrum covers everything from cosmic rays all the way to microwaves. Within the spectrum, we have visible light violets up to red. Above the visible spectrum are 4 ultraviolet wavelengths: UVA, UVB, UVC, and vacuum UV. While UVA and UVB rays are transmitted through the atmosphere, all UVC and some UVB rays are absorbed by the Earth's ozone layer. So, most UV rays humans encounter are UVA with a small amount of UVB. Let's take a closer look at these 4 wavelengths. Going clockwise from the left, we have UVA, which ranges from 400 to 315 nanometers. UVA is the longest wavelength, penetrating the deepest and causing age spots and wrinkles. Next, we have UVB, which ranges from 315 to 280 nanometers. UVB is the second shortest wavelength and is the main culprit of sunburn. Next, we have UVC, which ranges from 280 to 200 nanometers. It's the shortest wavelength and the most effective for disinfection. UVC rays do not reach the Earth's surface because they are entirely absorbed by our atmosphere. Finally, there's vacuum UV, which occupies the 200 to 100 nanometer range. Vacuum UV is strongly absorbed by water and air and thus cannot reach the Earth's surface. So what happens at that 253.7 nanometer range? Germicidal energy strikes a microbe cell wall and alters the cell's genetic material. Through a process known as photodimerization, UVC energy damages a cell's nucleic acids and protein structure, which causes 2 consecutive bases to bind together, forming a dimer lesion. You can see this illustrated in the yellow highlight on the right DNA helix. So, the 253.7 wavelength breaks through the cell wall, permanently damaging the cell DNA or RNA. Without this genetic code, microbes can no longer reproduce and are rendered harmless. A 2020 study published in the American Journal of Infection Control found that, just like measles, influenza, and many other viruses, the 253.7 nanometer wavelength is effective in deactivating the SARS-CoV-2 virus that causes COVID-19. Next, let's look at the actual size of common viruses. When we talk about coronavirus, influenza, or SARS, the mass mean diameter is 0.1 microns in diameter. To put this into perspective, a strand of human hair is about 50 microns, a dust particle is about 10 microns, and air pollution referenced in the graphic as PM or fine particulate matter is 2.5 microns. Our targets are significantly smaller than all of these. A coronavirus cell is an average 0.11 micron, so it acts more like a gas than a particle. It floats around and can stay airborne for very long periods. In fact, the microscopic size of airborne pathogens makes UVC so effective. Viruses and vegetative bacteria, which are smaller in size, can penetrate some HVAC filters. Ranging in size from 0.1 to 1 micron, Viruses and vegetative bacteria, including the current SARS-CoV-2 virus, are very susceptible to germicidal energy. Alternatively, fungal and bacterial spores, larger than 1 micron, are also susceptible to UVC. Because of their relatively larger size, spores take longer to inactivate, or a higher dose of UV is needed. Remember that these microorganisms are not typically flying by in the air, but growing in the dark, moisture-rich areas like coils and drain pans. These areas are treated as a surface UV application where we don't need a ton of UV energy since we have an infinite amount of time and length of exposure. Unlike a moving airstream where a pathogen is rushing by, a cooling coil is stationary, absorbing UV irradiation around the clock, 24/7, 365. Because of the diverse range of bacteria size and susceptibility, a growing number of building engineers are opting for a combination of filtration and UVC systems to address potential pathogens. And these microscopic viruses and bacteria can be spread by an infected person. People can also become ill by inhaling aerosol particles and respiratory droplets expelled by an infected person through talking, coughing, and even breathing. Transmission of the SARS-CoV-2 virus and other airborne pathogens can occur at distances greater than the 6-foot social distancing precaution. Large respiratory droplets settle out of the air quickly, within a matter of seconds to a minute. Smaller and very fine droplets, however, can remain airborne for hours. To combat this, building engineers use ventilation systems to control infectious particles. Remember what we said earlier. Ventilation, filtration, and UVC are 3 scientifically proven means of reducing pathogen spread. Concentrations of airborne pathogens are offset by introducing fresh outdoor air to dilute interior space air and then exhausting that amount as contaminated air. A rule of thumb is 2 to 5 air changes per hour, but as this chart illustrates, different building types require more frequent turnovers of room air. Most commercial HVAC systems are limited by the amount of outside air they can draw in. Due to the significant energy costs of conditioning additional outside air, many facility managers turn to filtering recirculated air and raising equivalent air changes per hour. Upper room UVC fixtures can provide a space with the equivalent of up to 10 air changes per hour. The photodimerization process we discussed a few minutes ago relies upon a ratio of time and intensity. In other words, how much resonance time a pathogen is exposed to the UVC energy will determine how much UVC intensity is required. Researchers report the effectiveness of UVC disinfection as a microorganism-specific rate constant, or K value, or the dose at which the microorganism is inactivated. We start with this pathogen rate constant, sometimes expressed as a K or Z value. The rate constant tells us how much UVC energy we need to achieve a specific inactivation level in a single pass. It's important to note that each subsequent pass of recirculated air further reduces pathogen concentration levels. As you can see from this equation, many operational and site-specific conditions impact the pathogen inactivation rates. Our sales engineers do a lot of these calculations for you. We can use computer modeling to achieve the necessary germicidal dose to inactivate the desired pathogen. Now, let's look at some of those operational and site-specific conditions that impact residence time. First, we need to know the volume and velocity of air traveling through the air handler. A higher volume of air, or faster moving air, requires more UV intensity or a longer duct run. More UV lamps or a longer travel distance will increase pathogen residence time. Next, we need to know the air temperature in the facility. Cold air reduces the output of UVC lamps, so that becomes part of our equation. Finally, we want to factor in the reflectivity of the plenum. Many reflective metals boost UVC dose as the germicidal wavelength bounces throughout the plenum and remains in play instead of being absorbed by the surfaces. There are 3 primary means of applying UVC against infectious agents: HVAC airstream disinfection systems, upper room or upper air luminaries, and HVAC coil-surface irradiation systems. It should be noted here that our late founder and respected industry leader, Forrest Fensel, pioneered the modern application of germicidal UVC in HVAC equipment nearly 25 years ago. Indeed, Forrest and his team collaborated on 17 UVC technology patents and several ASHRAE handbook chapters related to ultraviolet air and surface treatment. Clearly, he was a driving force in making UV resources the UVC disinfection and HVAC efficiency market leader. UVC airstream fixtures, sometimes called in-duct disinfection, are installed in an air handling unit plenums or in HVAC ductwork to inactivate microorganisms on the fly as well as on HVAC surfaces. A UVC in-duct system reduces airborne pathogens on each HVAC cycle, which can disinfect a room's total air volume several times each hour. Typically, these systems run year-round or during all HVAC operation cycles. Here's a computer simulation of a classroom.
Since the onset of the COVID-19 pandemic, UVC light or electromagnetic energy in the germicidal UVC wavelength has become a key technology in mitigating the spread of the deadly virus. The technology's popularity dates back nearly a century when scientists discovered that the sun's UV energy destroys germs and bacteria. In less than a second, UVC light can inactivate pathogens, essentially neutralizing infectious diseases. To illustrate how easily infectious pathogens can spread, we used a computer simulation to model a student sneezing in the middle of a classroom. The simulation shows what scientists already know. Aerosols expelled during coughing, sneezing, or even talking can travel with room air more than 30 to 40 feet. This same process occurs repeatedly in commercial offices, restaurants, grocery stores, TSA checkpoints, and doctor waiting rooms. To determine the effectiveness of UVC upper room fixtures, we conducted a side-by-side comparison of two classrooms, one fitted with germicidal UVC fixtures and the other without. These wall-mounted fixtures shine ultraviolet light across the top portion of a room, safely above people's heads. During this simulation, notice how quickly infectious aerosols are inactivated in the bottom classroom, which is fitted with upper room UVC fixtures. The germicidal energy renders harmless the majority of the airborne pathogens. The infection mitigation impact of the germicidal fixtures becomes clear. In spaces without UVC, such as the top classroom, contagious droplets can linger for several minutes, and the longer someone is exposed to viral particles, the more likely they are to become infected and allow further spread of the disease. Here's how it works. Upper room fixtures use the natural rise and fall of convection and mechanical air currents to lift pathogens overhead and into the UVC zone. The 253.7 nanometer UVC wavelength attacks a germ's DNA or RNA, rendering it harmless and unable to reproduce. And since the UV energy is overhead, occupants are safe to go about their normal business. In fact, this natural disinfectant works so well that the CDC and ASHRAE recommend UVC to slow the spread of the deadly COVID-19 disease. By eliminating airborne allergens, bacteria, and viruses, upper room UVC fixtures stop pathogens cold. They're perfect in emergency rooms, nursing homes, doctor's offices, classrooms, or anywhere groups of people congregate. To recap, UVC inactivates infectious microbes, leaving them unable to reproduce. Upper room UV fixtures installed near a room's ceiling neutralize microbes as they circulate. Upper room UVC fixtures have a long, scientifically proven history of inactivating airborne pathogens, with concentrations further reduced with each subsequent pass of recirculated air through the upper room. Mother Nature's own germ remover, UVC, helps halt the spread of airborne diseases, so people are safer and healthier. Contact UV Resources to learn more about the Glow series of upper room fixtures.
One of the oldest applications of UVC for space infection control is upper room fixtures. In the 1930s, researchers installed upper room UV lamps in suburban Philadelphia day schools to combat the spread of measles. They then compared infection rates to schools without UVC Schools that had the air sanitizing equipment experienced a 13% infection rate, compared with 53% for the population at large. Upper room UVC fixtures generate a germicidal zone near a room's ceiling where the natural rise and fall of convection or mechanical air currents lift pathogens overhead, where they are inactivated in a matter of seconds. Since UVC energy is overhead, upper room fixtures are safe for occupied spaces. In this video, see how UVC keeps cooling coils clean to boost HVAC capacity, save energy, and lower maintenance.
For years, building managers and HVAC technicians have battled to control indoor temperature. Once an HVAC system is installed, an insidious biological enemy starts chipping away at heat transfer efficiency as mold and biofilm build up on the coils. Left untreated, these little organic monsters slash heat exchange efficiency by nearly 15%. This results in up to 25% higher HVAC costs, in addition to very uncomfortable occupants. Think of mold, biofilm, and other organic compounds like a layer of insulation. The thicker that insulation, the harder your system must work. To meet demand, operators often attempt to compensate by speeding up fans, pumping more chilled water, or lowering system water temps. But many HVAC insiders have turned to germicidal lamps to remove microbes from fouled coils and guard against their return. UVC energy disrupts the microbe's DNA, so this zombie apocalypse is never going to rise from the grave. Whether your system is brand new or has years of accumulation, the germicidal wavelength kills microorganisms dead. It's hard to imagine that a few UVC lamps can protect cooling coils, but scientists haven't found a microbe that can withstand Mother Nature's own germ remover. Once the microbes are eliminated, the conditioned air gets better, cooler, and cheaper. Installation is easy and costs less than 15 cents per CFM. Once installed, UVC lights patrol your HVAC system around the clock. Maintaining them is literally as easy as changing a light bulb each year. Okay, quick recap. Damp, dark spaces breed coil-clogging gunk, restricting air and heat transfer. If UVC light is installed, it kills the gunk, cleans the coils, and restores system efficiency. Costs decrease and air quality is restored. The occupants are happy and the bottom line is happy. Find out how germicidal fixtures from UV Resources can help you save costs and boost efficiency right now. Visit us at uvresources.com/save energy or call us at 1-877-884-4822 to learn how easy it is to put UVC light to work for you.
Perhaps the most common UV HVAC application is for cooling coil irradiation or coil cleaning systems. These fixtures are designed to destroy biofilm, bacteria, and mold on HVAC coils, air filters, ducts, and drain pans, and prevent these areas from becoming microbial reservoirs for pathogen growth. While not explicitly designed for airstream disinfection, an HVAC surface irradiation system can also provide first-pass inactivation ratios of airborne pathogens of up to 80%, along with the primary benefits of restored cleanliness, improved heat exchange efficiency, and lower energy use. And, as pictured here, a coil maintenance application requires less UV energy than on-the-fly applications due to the extended residence time. In other words, unlike a microbe in a moving airstream, the cooling coil is stationary and absorbs UVC energy around the clock. UVC's germicidal effects are well proven in research dating back nearly a century. Many government agencies and professional associations offer guidance on the germicidal wavelength, including ASHRAE's 2020 Systems Handbook, its 2019 Application Handbook, and the current 2018 ANSI, ASHRAE, and ACA Standard 180 for building systems. This latter standard establishes minimum HVAC requirements for acceptable comfort levels, energy efficiency, and indoor air quality standards in commercial buildings. ASHRAE's position document addressing airborne infectious diseases notes that upper room UVGI and in-duct air handler UVGI systems offer many applications. As such, ASHRAE puts high application and research priorities on both types of UVC installations. Scientists know that UVC alters the genetic structure of microbial DNA and RNA so that cells can no longer reproduce and are rendered harmless. ASHRAE's position document on infectious aerosols identifies germicidal UVC energy as a proven method of controlling airborne infections alongside ventilation and particle filtration. Both the U.S. Centers for Disease Control and Prevention and ASHRAE include UVC as a recommended mitigation step to slow the spread of the SARS-CoV-2 virus. While hundreds of scientific studies over the past century have proven the disinfectant efficacy of UVC, ASHRAE cautions that some newer air purification technologies do not enjoy similar peer-reviewed research and support. ASHRAE and the International Ultraviolet Association are partnering to advance UV research and technologies. Last year, the groups agreed to develop necessary data, protocols, guidelines, and standards to ensure UV efficacy and safety to improve indoor environmental quality. Other areas of potential collaboration include general advocacy, joint conferences and meetings, education and professional development, and academic research. Now that we understand how UVC can be applied, it's important to consider ventilation and filtration technologies as two scientifically proven means of reducing pathogen spread. Most energy experts recommend that facility engineers and building managers use multiple preventative infection control measures so that whatever pathogen is not mitigated by one method, say filtering, is inactivated by another, say UVC. In fact, the ASHRAE Epidemic Task Force endorses flexibility in meeting its standard by stating, quote, air cleaning technologies can be combined to produce the desired MERV 13 equivalent level of air cleaning. So the Epidemic Task Force recommends that we target the pathogen removal rate equivalent of a MERV 13 filter. However, not all AHU systems, particularly the large number of aging systems, can handle the high airflow restrictions and static pressure of MERV 13 or HEPA filters. So, working with microbiologist Wally Kowalski, who literally wrote the handbook on UVGI, we modeled 3 separate filtration options. Together, we looked at the pathogen removal rates of a MERV 8 filter only, a MERV 8 filter combined with the typical UVC cooling coil system producing a UV dose of 3.3 joules per meter squared, and a MERV 13 filter only. And what we found is really surprising. Facility engineers can achieve that MERV 13 removal rate equivalency by combining a medium efficiency MERV 8 filter with a standard coil cleaning UVC. And because there is less airflow resistance using a MERV 8 than a MERV 13 filter, facility engineers do not need to sacrifice airflow levels or compromise cooling capacity to achieve a near MERV 13 level. So, let's take a closer look. A typical UVC install on a cooling coil system would roughly be 7 to 10 watts per square foot. As we can see with this chart created by Professor Kowalski, combining a typical coil irradiation system with a MERV 8 filter achieves up to 78% inactivation for the SARS-CoV-2 virus. That single pass removal inactivation rate is very near the predictive 85% performance of a MERV 13 filter recommended by ASHRAE, shown here in red above. So this hybrid filter and UV combination is 92% as effective at removing pathogens as the targeted MERV 13 filter. We can drive even stronger performance if we increase the germicidal dose beyond the 3.3 joules per meter squared without compromising airflow rate. Importantly, this hybrid combination of air cleaning technologies can also save energy due to the lower pressure losses associated with the MERV 8 filter. Again, the MERV 13 filters have a greater resistance on higher pressure drop, the more energy it takes to move air through the filter. There are several options for installing UV lamps. Ideally, lamps are installed downstream of the cooling coil for both air disinfection and coil cleaning. A coil maintenance application requires less UV energy because the coil is stationary. In the case of a moving airstream, however, pathogen resistance or exposure time is limited to fractions of a second, so UVC intensity must be substantially greater. In this example, we've added more UV lamps to increase the germicidal dosage or intensity. Because cold air can reduce UVC lamp performance, engineers can install UV fixtures upstream of the cooling coil to leverage the warmer operator environment. In fact, moving UVC lamps from 55-degree temperatures, which is typical of a downstream installation, to a balmier 75 degrees, which is common in an upstream environment, can raise a UVC lamp's output by as much as 30% or more. Note that if you do install UV lamps upstream, you should specify UV-safe filters. The best takeaway is to install the UV lights where you have the most inline space to maximize exposure or residence time. So let's recap what we've learned about germicidal UVC. UVC is proven to destroy pathogens, inactivating microbes in less than a second. In general, the effectiveness of UVC air disinfection boils down to time and intensity, or said differently, how much time or duration a pathogen is exposed to the UVC energy. UV has been around for 80+ years in upper room applications and more than 30 years in airstream and in-duct applications. ASHRAE devotes 2 handbook chapters that discuss the benefits of UVC. There are also 2 ASHRAE test standards covering UVC. 185.1 tests airborne or on-the-fly disinfection, and 185.2 tests coil and surface performance. 3 ASHRAE position documents also support this technology. And remember, UVGI HVAC technology is extensively peer-reviewed. However, many other air treatment products are not well validated, independently tested, or researched.